Morning at 8:40. Yeah. So instead of starting at 9 tomorrow, we will start at 8:40 with the talk of Colin McDonald. So now our next speaker is USHENKO. He will talk about the measurement of a small light absorption in microparticles by means of optically induced rotation.
Good evening. I'd like to present the final report for today, titled Measurement of Small Light Absorption in Microparticles by Means of Optically Induced Rotation. I try to be short but concise. So this is our group, consisted of the head of group, Professor Angelski. He can't attend, unfortunately, and kindly asked me to present this research. This an international group, consists of Ukraine, Denmark. Let's start with this is our city in which we live and work, the main building of university, you can see here. Town, pretty good name, Chernivtsi, with beautiful churches, theaters, and so on. So let's start with an introduction. So what is the problem of this research? The problem is determining of optical constant of micro and nanoparticles. It is very pertinent for numerous applications. Particles of different sizes and nature are widely used in detailed investigation of optical fields, in studies of microscopic properties of fluids and biological specimens, in atmospheric aerosols and interstellar dust. All these activities require, among other important physical information, the knowledge of the particles' optical properties and their dependence on various external conditions. In general, the well-known parameters of bulk materials are not applicable for very small quantities of the same substances. Even in cases where the expected size-dependent factors are negligible, the specific conditions of small particles formation must be taken into consideration. In most cases, the optical constant are used for modeling of effects associated with light scattering, extinction, absorption, by isolated particles and their ensembles. Consequently, it is necessary to search the techniques based on data for light scattering, because the conditions under which the optical constant are measured are close to the condition for which they will be applied. Within the frame of these techniques, the most powerful existing methods are based on a comparison between the experimental and theoretical data for the angle of distribution of light scattering by an isolated particles, relying on scattering. In this case, it is possible to find the particle radius, real and imaginary parts of refraction index, and even the particle structure, accepting that the particle consists of the core and the shell with different optical properties. This method is comprehensive and informative. However, a large number of measured parameters usually obscure the fitting procedure. This calls for the search more specialized methods aimed at more specific parameters whose influence on scattering characteristics is more explicit and can be derived immediately. Possible ways for realization of this are associated with the mechanical action of light on small particles. Due to the intensive development of technique for optical trapping and manipulation, it is not difficult to observe and to measure the characteristics of motion of microparticles suspended within an optical field. Such approaches provide suitable tool for evaluation of the mechanical ponderomotive factors, namely force and torque, which an optical field exerts on a particle. The ponderomotive factors can be directly associated with the optical parameters of the particle, and this can be employed for the measurement. For example, within the framework of theory, the optical force F and torque T acted by playing on a chromatic wave on a homogeneous isotropic spherical particle are directed along the wave vector and determined by the following expression with flow density, wave frequency, velocity of light in vacuum, wave number, spin number. It can be presented from this reference, where A and B sub L is mean scattering coefficients. These equations describe the situation in which the particle is assumed to be immersed in a homogeneous isotropic dielectric medium with real permittivity and real permeability. Given the relation are applicable for inhomogeneous field if the spatial scale of the inhomogeneity of the incident beam sufficiently exceeds the radiation wavelengths and the particle size. This requirement is violated in typical optical trapping situation where the particle is localized within a strongly focused laser beam with near wavelength transverse size. Then the above equations should be modified. For example, if the particle is placed on the axis of Gaussian beam, we can write down the following expression for the torque with the normalization constant, beam power, intensity. W sub 0 is the waist radius of the beam measured at following amplitude level. These coefficients originate from the Gaussian beam expansion in terms of vector spherical wave functions. Here, that sub 0 is the distance between the particle center and the waist of a beam. The scattering coefficients A and B represent the electric and magnetic multiple polarizabilities of the particle in this form. The analysis of the last equations show if the particle is non-absorbing, it experiences no torque. We write down the equation for the optical force and torque in lowest order approximation, keeping only the electric terms in this form. The optical force being proportional to the imaginary part of the polarizability appears due to the particle absorption. At the same time, the imaginary contribution to the polarizability of non-absorbent particles can exist because of the radiation friction effect, due to which we have this form for this coefficient, where alpha in the 0 power is the static polarizability corresponding, whereas the k is 10 to the 0. Some facts, thus torque is exactly 0 for the non-absorbent particles. In this case, there is no imaginarity connected with the phase difference between external electric field and the field-induced dipole moments. External spin acts on a spherical particle only if it is absorbed. Accordingly, the torque felt by a particle in a circularly polarized way will facilitate the selective and sensitive measurement of the particle absorption. The advantage of using the field-induced torque is that the manifestation of any torque is the spinning motion of the particles, whereas a force can be detected via its translation. The force varies from point to point, making it difficult to establish an immediate correspondence between the force and the particle trajectory. Quite oppositely, the spinning particles preserves its position. It can be easily stabilized by optical trapping technique so that the field action is stable and well controllable. So let's start with the experiment. Here you can see this optical scheme of experimental setup, in which the linearly polarized beam from the semiconductor laser goes from the special filter with a pinhole form Gaussian type laser beam. For its quarter wave plate, 5 it's a objective which focus the laser beam on the cuvette 6 with microparticles suspended there, and the CCD camera 9. Overall losses of the laser beam power in this system were estimated as about 30%, resulting in the maximum power in this cell it appears to be 100 milliwatts. During the measurement, one of suspended particles is trapped in the Gaussian beam's focal region. The motion of the particles is observed and registered by the projective system 7 and 8 and CCD camera 9. The images are transmitted to the computer 10. It performs the image analysis and processing. It also provides a possibility to control the laser power, quarter wave plate position, and orientation. There are several important conditions should be fulfilled in order that the field-induced spinning of suspended particles is observable and metrologically consistent. The first one, the viscosity of suspending medium must be small enough. In the current experiment, distilled water was chosen with dynamic viscosity of this form at room temperature. Secondly, the refractant particles with low reflection are preferable because this will be trapped within the maximum of Gaussian beam, implying that the particle refraction index exceeds that on water in this form. For efficient concentration of laser beam energy on the particles, strong focusing with a high numerical aperture objective is desirable. However, in this case, the measurement process becomes sensitive to small deviation of the beam waist from the nominal value. This is why moderate strength focusing macro objective is employed. For the efficient trapping of the particle should be several times the particle size should be several times smaller than the focal spot. But the particle size shouldn't be very small compared to the radiation wavelengths. The tested particle should possess rather low absorption to avoid local heating. To satisfy all this condition, weakly absorbent dielectric particles with diameters from 0.5 to 2 micrometers are appropriate with this absorption. This video demonstrates the spinning motion of trapped particles. Fragment A shows rotation of weakly absorbing latex particles illuminated by a beam with a stable maximum power of 100 milliwatts, with initial laser beam power of 140 milliwatts. Gaussian particles of comparable size have higher absorption, fragment B, and spin with higher velocity. Besides, this video clearly shows the spinning rate dependence on the laser beam power, from minimal to this minimal one, and power is increasing. By means of such videos, the spinning velocity can be easily determined with a high accuracy is about 1%. It is proportional to the incident beam power expected from the theoretical consideration, and from the data of this video is confirmed by the figure 4. Here you can see the spinning rate of Gaussian particles of video. B for the experimentally measured and theoretically calculated. The method analysis and validation. The spinning motion is due to the field spin angular momentum absorbed by the particles, and its angular velocity omega is related to the radiation torque by the following equality, where eta is the dynamic viscosity of the medium. This figure presents the behavior of absolute torque and the angular velocity as a function of the imaginary part of the refraction index k for a particle suspended in water and trapped in the center of focused Gaussian beam. This figure indicates the distinct relation between the particle spinning in a circularly polarized light and its absorption. This relation is close to linear with high accuracy. You can see that in this inset, which is affordable for many metrological practices because of potential laser calibration and direct interpretation of the measuring results. In fact, the thick red line in figure 5 shows that absorption index k of the particle can be directly derived from the absorbed spin and velocity omega exhibited by the particles in the beam with the power p by means of this relation. Now consider how the measurement efficiency can be affected by other factors such as the beam power and the beam waste size. The particle size is seldom known with a high accuracy. Even usage of monodispersed powder for preparing the particle suspensions does not prevent random deviation of the diameter of any given particle from the nominal level. As it can be seen from this fragment A in this figure, the field-induced spinning velocity changes slowly within unit of percent in the working range of the particle radii from 0.3 to 0.7 micrometers. As it has been shown, even though the optical torque appears as a selective sensor of particle absorption, its sensitivity depends on other optical parameters. It is impossible to recover the exact numerical value of absorption index without knowledge of real refraction index. This feature is illustrated in this figure, fragment B, where it can be seen that the plus minus 6% indeterminacy in these parameters produces plus minus 10% inaccuracy of the absorption measurement. For condition of moderate focusing realized in our experiments, the particles cannot be optically stabilized in the longitudinal direction. In the experiments, this difficulty is overcome by having a small longitudinal thickness of the cell, it's about 70 microns. The floating particles are trapped at a certain distance from the back wall by hydrodynamic and photophoretic forces. If a particle is trapped, its longitudinal position coincides with the waste plane with an inaccuracy it doesn't exceed plus minus 10 microns. It may suppress the spinning rate up to 20%, which is demonstrated in the following figures. In our experiment, we used the epoxy resin for two regions. The first one, these materials allow generation of monodispersed droplets with appropriate sizes. And the second one, it can be prepared in form of thin film, whose optical constant can be easily measured by the standard procedure. There is the help of spectrophotometer and the refractometer. For epoxy resin, we have the measured following parameters. It used in this table in first row, like a calibration procedure. Knowing the particle's complex refraction index, the third and the seventh columns of the table, and Gaussian beam parameters, it is possible to calculate transition coefficient Q and theoretical spinning velocity omega. The measured value of the spinning velocity is close to the theoretical value, and the difference of about 20% is not negligible. We associate this difference with the above discussed factors. First of all, longitudinal displacement of the particles in comparison with the beam waste. An additional contribution to this difference is the deviation of cell temperature, due to which the water viscosity exceeds the accepted value. Our experiments have shown that such a decrease of spinning velocity, as compared with the theoretical predictions, repeats systematically, and it can be accounted by the normalization coefficients mu. This one. This coefficient facilitates a reduction in the measured data obtained for all types of particles to the standard condition. The data presented in the fifth column can be obtained from the data presented in the sixth column, measured by multiplication by unity point 21. The calculation of omega and Q gives the possibility to find the absorption indexes presented in the seventh column, which completes the measuring procedure. Let's start with the conclusion. In this work, we describe a special approach based on light-induced particle spinning, which enables directly measuring the light absorption of microparticles. The study of mechanical motion of microparticles trapped within optical fields offer a lot of new interesting possibilities for metrology of their optical properties, making the present report as a first step in this direction. At the present form, the approach is specialized and aimed at determining the particle's absorption, provided that other optical parameters, namely real part of refraction index, are known. Such a situation is typical for a weakly absorbing dielectric particles. we can speak about the relation between the particle spin in motion and its absorption index. The absorption characteristics had been derived from the optical force data regulated by the total imaginary polarizability. An additional benefit of this method is the linear character of the indicative dependencies. Of course, this linearity is only preserved for a small absorption. K is proportional to this value or less. But this is just the typical condition for observed dielectric particles. Important question emerged on the limits of absorption that can be measured by this method. The lower limit of the detectable rotation velocity is restricted by the natural instabilities of the particle position and orientation caused by stochastic influences. Let it roughly be 0.1. A reasonable maximum of a beam power in view of possible self-induced effect in suspended medium may be taken up to 1 watt. The minimum measurable absorption index appears to be 4 multiplied by 10 and minus 7 power. The upper limit can be determined by the conditions that the absorbed energy does not change the medium's parameters and is homogeneously distributed over the particle volume. Both requirements lead to a conclusion that reliable results can only be expected while K is less than 10 in the minus 2 power. In real situation, proper optimization procedure can noticeably improve our present results. Even in its simplest form described here, the method demonstrates high sensitivity and good prospects for the accuracy improvement associated with due calibration and stabilization procedures. It is to be expected that the proper control of the beam power and the cell temperature, the suspended medium viscosity, and the particle longitudinal position will make the proposed method a suitable way for investigation of weakly absorbed particles. Thank you.
Time for questions. No questions?
Everyone is tired.
Everyone is
tired.
There's no time for
What? So if that's the case, let's thank the speaker again. But we are done, right?
Yeah, thank you very much for being patient and staying in the audience. Unfortunately, we were not strict with our time schedule, so we will start tomorrow a little bit early at 8:40. So the first presenter will be Callum McDonald. Excuse us to be being late. And now you are all invited to it's the direction like we go to the cafeteria. Now we go to Salon d'Honneur. There will be poster session which will be combined with the reception cocktail. So you first drink and eat, and after there should be 14 posters, and the SPA student chapter who helps us to organize this poster session, they will organize the voting procedure. So we have to choose the best poster, and the winner will get award. The student chapter will give its credit to the winner. So I invite everyone to join our cocktail, and don't forget, tomorrow it's not 9, it's 8:40.